Hello, everyone. I'm Jindřich Minář from R&D IT Data Infrastructure at MSD, and together with my colleagues Jan Rosecký, Vinny Antonucci, and Jan Nešpor, I would like to present the simplified JSON-LD representations of linked data based on allotrope models. Let me preface this by saying that this presentation showcases our experiments rather than any production applications. First, I would like to spend ample time explaining our motivation. Then I will show what JSON-LD can do step by step. I would use a running example for that. And finally, I want to leave plenty of time for questions. So let's set the scene by talking about developer experience. And developer experience is defined as user experience of developers, and I like that. In this definition, it says that it focuses on perceptions of utility, ease of use, and efficiency. Good DX is considered to contribute to technology adoption and productivity. For example, when you have zero learning curve or faster ramp-up time when you are onboarding new developers. And for the most part, it is a property of interfaces through which developers work with a technology. So in a broad sense, these interfaces may include things like APIs, programming languages, community support, or even documentation. And I think it is important to approach developer experience not with some patronizing charity, but really with solidarity, recognizing the limited time everyone has and the different stages of learning where they are. So I would venture that allotrope standards may be considered challenging from the perspective of developer experience. I think we have this curse of knowledge, not really realizing what it is like not to know something. And I think when balancing machine readability with human readability, allotrope standards had to make some difficult trade-offs. So first up, I would say there is a knowledge gap between the usual knowledge that developers have and the ADF's maybe unfamiliar data processing model. At first sight, ADF is a black box. It's a binary format that requires custom tooling to work with. Terms in AFO are referred to via opaque alphanumeric identifiers instead of human readable names, such as this QNMR purity result instead of the alphanumeric ID. And this might not be a problem, like in the architecture of web. One of the sentences there is that the web was designed so that agents communicate resource information state through representation, not identifiers. So that's one of the principles of REST. But opaque identifiers are impractical for communication between people. There's also verbose modeling patterns. For example, you have the BFO alignment that reifies lots of the classes. And consequently, I would say that ADF data is difficult to understand and manipulate directly. So the question, I think, is, can we expose a simpler interface for ADF data? One that helps developers with understanding and manipulating it indirectly, all the while preserving the benefits of interoperability with a broader family of allotrope standards and the standards the allotrope standards are based on. So in this presentation, we demonstrate how JSON-LD can serve as such an interface. JSON-LD is a JSON syntax for RDF and an API for data manipulation that's standardized in recommendations of the World Wide Web Consortium. It is interoperable with common data processing toolchains. The API enables round-tripping back to other RDF serializations. And it preserves the key distinguishing feature of RDF, which is explicit links between data and metadata. So as we learned in the last presentation, I think data in JSON-LD can be considered a self-reporting asset that you can understand without out-of-band information. And it is designed actually to improve the developer experience of semantic web technologies. The World Wide Web Consortium also recognized that the developer experience is important and came up with JSON-LD. And I think the key value is that it provides reach. That is, reach to developers with limited knowledge of semantic web standards, and crucially to tools that consume JSON. Here I would just go over two basic key operations of JSON-LD API, which are compaction and framing. JSON-LD compaction is an operation that reduces verbosity of data by referring to a static shared context of data exchange. The context, it defines local aliases or some syntactical shortcuts that allow making data compact and simultaneously unambiguous. So the context basically maps what data says to what it means. In the context of this presentation, I refer to Allotrope data format as ADF, and I don't need to explain what it is. Here, ADF is defined as a compact JSON-LD term that may be expanded to Allotrope data format, which in turn can be expanded to its identifier. Here, I'm just using the URL of the specification. JSON-LD framing is an operation that coerces graph data into a hierarchical tree with a predefined structure, with a given predefined structure. It basically replaces the links with nesting, which allows you to access data by index-free traversing rather than pattern matching with SPARQL queries. With the help of framing, JSON-LD makes data map to native data structures, such as hash maps or arrays that are available in most popular programming languages. And I think not everyone wants to embed a SPARQL query engine just to run pattern matching queries in their applications, just to navigate the data. So the scope of our work that I will be presenting here, it's limited to a human readable representation of just the ADF data description of simpler tabular model. ADF data cubes or other parts of ADF files are out of the initial scope. And the main contributions are a method to derive a JSON-LD context from Allotrope Foundation ontologies, and another method to derive JSON-LD frames from Allotrope Data Models. Basically, once you have the context and the frame, then you can use any standards compliant JSON-LD processor, use the context and the frames, and produce JSON views of ADF data for straightforward consumption by both people and machines. The running example that I'll be showing uses a fragment of test data for the QNMR model, which is a Allotrope recommendation as of March this year, and shows step-by-step some ways in which the JSON-LD API can make ADF data easier to understand and manipulate. So we start with ADF. ADF is a binary file format based on HDF5. It requires ADF API to be read, which means Java or C# library, or Python in the near future, as we might learn in the upcoming presentation. Here it is portrayed via the HDF view application and doesn't really tell us much. This immediate interface doesn't really reveal the wealth of what we know about the data that is already available in the Allotrope Foundation ontologies and data models. Next up, we can use the ADF API to turn the HDF5 into RDF and basically map the HDF5 data structures for ADF data description to an RDF view that can be serialized as text, for instance, here in RDF turtle syntax. Still not particularly readable, but at least it's text and you don't have to use a specific application to read it. You can make it prettier with namespace prefixes. So that's a little bit more compact. And we can transform it into JSON using JSON-LD API, which produces this JSON view, which is at this point not really much better than what we saw before. But we can improve it step by step. So We can use the namespace prefixes just as in the turtle syntax to make it more compact. We can also alias identifiers. We can use the preferred labels of AFO terms as aliases. So on the left, you see the context of the data exchange that creates these aliases like QNMR purity result for the opaque identifier. And on the right, you can see the fragment of QNMR data, which now uses these more readable aliases so that you can figure out or at least have some rough idea what's the data about. It's an NLI document which features some QNMR purity result in %. So here there are some caveats for AFO. JSON-LD terms have to be unique, so some preferred labels from AFO have to be disambiguated by domain, such as table as equipment and table as arrangement of data. Other terms, such as time, may conflict with namespace prefixes defined by AFO. So we have to deal with that, and when generating the JSON-LD context, take that into account. You can go one step further and alias the units. So what if we want to compact units with their symbols? In JSON-LD, the terms are only used for expansion of vocabulary relative positions, and the IDs are considered document relative, so they don't use the term definitions for expansion by default. But if we use this type vocab to make values of has unit vocabulary relative, we can allow their aliasing with unit symbols. So the $sign is now shown as the value of has unit attribute. With framing, we can coerce the data into an ADM specified hierarchy. The Allotrope data models already prescribe what shape the conforming data must have. They connect the target classes by specific properties. And if we want to embed the graph data into a hierarchical tree, we can even introduce reverse properties. So instead of member of, we can introduce has member to just start at the NLI aggregate document and go to NLI document and then to the final result, which might be what we want. So here we actually want to, well, we can produce the full views or some tailored partial views of subsets of ADF data descriptions, which might be, well, the full views might be challenging to produce for graph models. So further on with compaction, we can use this for navigating the AFO, like the specific classes in AFO with type indexed properties. The AFO tends to specialize classes instead of properties. So the tabular models, for instance, contain subclasses of information content entity. However, distinguishing values of a generic property, such as has facet by their classes, requires loops and filtering when navigating data. So to simplify the navigation in such data, we can actually index the values of those generic properties by their class. So here, instead of scanning the values of has facet, we can index it by this container type with the type and just access the QNMR purity result directly, which might be a little bit easier. Further on, there might be a largely cosmetic change. We can alias the JSON-LD keywords. If you don't like the @ sign, you can use some custom aliases, but actually this has quite practical applications. For instance, for reusing identifiers. So I tend to alias @ID as _ID when I'm indexing the data in Elasticsearch. And the problem, or well, JSON-LD offers many more ways how to make data compact and predictable. For example, you can specify the data types of property values, you can lift them from data to the JSON-LD context. Like data types of generic properties such as has value can be actually scoped within a specific class. And we can also close the world with explicit inclusion flag in JSON-LD frames to ignore the inverse properties. So here you can get rid of the member of, for instance. While this is extensive, these ways are limited by the scope of their JSON-LD standards. So if we want to go beyond what JSON-LD API allows, we need to implement custom post-processing, such as for removing redundancies. And here, this example shows the UID-based URNs as identifiers, which is what the ADF API generates. And while they allow linking from other data, they are generally treated as local identifiers. They are scoped to a given ADF file, so similar to how RDF treats blank node identifiers. And those can be elided for nested objects via JSON-LD framing. So finally, with not so much loss of meaning, we can actually have this compact JSON after the post-processing. That might be much more easier to read and understand than the initial ADF file or RDF representation that we've started with. There are some limits of JSON-LD for AFO and ADM in particular that I've encountered. So the slashes are not supported in JSON-LD. So for instance, they are present in unit symbols such as cubic centimeter per minute, but they can be replaced with supported characters. So we can say cubic centimeter per min instead. And as I mentioned before, the JSON-LD terms have to be unique. So some AFO terms are just disambiguated by the domain. JSON native data types are only available for booleans, integers, and doubles, but AFO uses others, such as ints. We cannot really omit the @id or the identifiers if not used for embedded blank nodes. So that's why I have used the post-processing. And we cannot redefine the reserved JSON-LD keywords, such as for type indexing of the graph. This is reserved by JSON-LD spec. So I'm actually at the summary point, which is good from the time perspective. Let me summarize what I've presented on two aspects. First is why we are doing this. And the reason is to really leverage the developer familiarity and tool support for JSON to enable easier consumption of ADF data without compromising the semantic interoperability that is provided by the standards, the Allotrope standards, the semantic web standards. And the second point is how we do it. So what we have done here is to create a mapping between AFO and JSON-LD context that can compact ADF data. We have created a method that can generate JSON-LD frames from Allotrope Data Models, prescribing the hierarchical structure of the data for easier navigation. And we can use ADF API to turn ADF data description into RDF, giving us plain text representation. And we can use a JSON-LD API to turn this RDF into JSON and back actually, and make it easier to work with using the generated context and the generated frames. This approach is totally generic. It's applicable to both tabular and graph models. However, just for simplicity, we started with the most simple tabular models. So with that, I think that's all I have today. Happy to answer any questions.